Hi, in this video we are going to learn about linear reservoir routing. Now in the previous video we discussed what linear and nonlinear reservoir means. So whenever storage has a linear relationship with outflow discharge Q, we call it a linear reservoir. Okay, so what I'm going to do is I'm going to draw a simple reservoir. Now in practice we may not necessarily route the flow through a reservoir, but we assume that what will happen if the flow goes through a reservoir and how the hydrograph will get routed. So let's draw a simple reservoir here, and let's say this is my input. So that's our input I, that's our outflow Q, and then we say that this is the storage in the reservoir, and as the inflow and outflow changes, the storage will change. Now we discussed in the lumped routing method or hydrologic routing method we need two set of equations. So one is the continuity equation, which is ds over dt is equal to I minus q, and the other expression that we need is some relationship between storage and discharge. So in that case this is going to be S is equal to KQ. Okay, now in any routing problem I is given to us. So let's assume that this is our inflow hydrograph and we have values given I0, I1, I2, I3, I4 and so on. So we can say that I0, I1, I2, I3 up to IN is given. So we know all the I values and we have to find Q, and then we say find Q0, Q1, Qn. Okay, so this is our problem. Our inflow hydrograph is known, we have to find the outflow hydrograph, and these are the two equations we have. So these are the two equations we need. Now the continuity equation we have is in continuous form, so I'm going to write a discrete form for that. So ds over dt can also be written as sj minus 1. So this is basically storage at current time step j minus the storage at the previous time step j minus 1 divided by delta t, and delta t is our time step. So we are given I0, I1, I2, I3. So whatever time interval we have between those values, that is our delta t. Similarly for it we can write the average of inflow values between the time step minus qj plus qj minus 1 divided by 2. So what we have here is a discrete form of continuity equation, and then we also have this relationship between storage and discharge. So what I can do now is I can write Sj in terms of K and Q. So Sj will become Qj minus Qj minus 1 divided by delta T, and Sj is Kqj, so I'm just going to say this whole thing is multiplied by K. Okay, and then we have Ij plus ij minus 1 minus qj minus qj minus 1, and then I'll bring this 2 on the other side. So what we have on the left hand side is 2k over delta t and qj minus 1, and this is the input and output between the time interval. So since we are interested in finding Q values, so what I'm going to do is I'm going to write an expression for Qj. So Qj will be the discharge value or the outflow hydrograph value at the current time step. So to do that, what I will do is I will get the 2k over delta t times Qj. This is this part, and then we have Qj here also. So this will be again Qj, and then I have ij plus ij minus 1 minus qj minus 1, and then I'll bring this qj minus 1 on this side. What I have now is 2k over delta t times qj minus 1. Okay, so let's simplify this expression. So what we have here is 2k plus 1 delta t times qj, and then we have ij plus ij minus 1, not use the parenthesis, and then we have plus sign qj minus 1 2k over delta t minus 1. Okay, so what I can do now is I can simplify this more. So I will have 2k plus 1 over delta t times qj is equal to ij plus ij minus 1 plus 2k minus delta t over delta t times qj minus 1. Okay, now what I can do is I can bring this delta t over 2k plus 1 on this side. So qj is equal to ij plus ij minus 1 times delta t over 2k plus 1 plus, now delta t will get cancelled, or maybe I'll just write it down and then we can simplify. So what we have here is 2k minus delta t over delta t times delta t over 2k plus 1 times qj minus 1. Okay, so delta t will get cancelled, and what we will have is qj is equal to delta t over 2k plus 1 times ij plus ij minus 1 plus 2k minus delta t over 2k plus delta t times qj minus 1, and we can simply replace this with a constant c1. This will be our constant c2, and if I do that, what I have is qj is equal to c1 times ij plus ij minus 1 plus c2 times qj minus 1, and this is the expression that we have to get the discharge hydrograph after routing when we have the inflow hydrograph. Now, as I said, I0, I1, I2, In is given or known. which means that this part is known to us. Okay, and also delta t is known, and then k is also given, or it can be determined, and we will learn later how to figure that out. So we are given delta t, we are given k, which means C1 and C2 are known. So the only part unknown is qj minus 1. What that means is if I'm solving for q1, I should know q0 should be known. And q0 is our initial condition. And as long as this initial condition is known, we can solve for q1. Once we know q1, we can solve for q2 after q1 is known. And once you know q2, you can solve for q3 and so on. So this is how the linear reservoir routing will work, and we will figure this out when we do a numerical example in the next video. But before we do that, let's also see what do we have. So the expression that we have for C1 is delta t over 2k delta t over 2k plus delta t, and then for C2 we have 2k minus delta t over 2k plus delta t. Now what I'm going to do is I'm going to write an expression that says 2c1 plus c2, and what that will do is 2 delta t over 2k plus delta t, and plus c2 is 2k minus delta t over 2k plus delta t. Now we have the denominator common, and if I add the numerator, what I get is 2k plus delta t over 2k plus delta t, which is equal to 1. Okay, so the condition we have satisfied for C1 and C2 is that 2C1 plus C2 is equal to 1. Okay, so whenever you calculate values for C1 and C2, we can check that it satisfies this condition. The other thing we want to remember about linear reservoir routing is that the amount of attenuation. So remember, we are trying to attenuate the hydrograph. So if this is I and you route the hydrograph, and what you get is Q. Okay, so this is the reduction we got in the peak, and the amount of attenuation is a function of delta t over k. So the amount of attenuation is a function delta t over k, and smaller the value of delta t over k, smaller the value of delta t over k, the greater the attenuation. So that is something we want to remember. And as I said, when we use this in practice, we don't necessarily route the water through reservoir. We just try to see how we can achieve the attenuation that we are seeing in the natural system, and then we can interpret the hydrograph and manipulate these values to match our observed data. The other last thing we want to remember is that the value of delta t over k should be less than or equal to 2. Okay, so if this condition is not satisfied, sometimes the Q values can be negative. So delta T Q over K should be less than or equal to 2 to avoid negative values of Q's. Okay, and this is it for this video. So we want to remember this expression to find values for Q's. We want to remember that 2C1 plus C2 should be equal to 1, and then finally the time step and the K values we use, they should satisfy this condition to avoid negative values. Okay, and in the next video we will use a numerical example to see how we can route a given hydrograph by using linear reservoir method. So that is it for this video. Thank you.